Hello there, we are STES Rocketry Team. I'm Aasit Vora, this year's project lead, and I hope everyone watching this video is in good health and spirits. For the 2021 IREC, we're Team 80, competing in the 10,000 feet COTS motor category with an APJ-III rocket and OATMEAL payload. This is the third attempt to take part in a similar category with a different payload from last flight event, and the goal has been to mitigate any and all mistakes that happened previously and to get all rocket phases right perfectly without compromising the production quality. Despite of the pandemic, the team has worked tirelessly from our homes to create a design that is as concise and fail-proof as possible. Following the legacy of its predecessor, APJ-III is a 7 feet tall carbon fiber fiberglass composite rocket with a 3U payload envelope and powered by a M-class COTS motor, which will help us get close to our desired apogee. Let's dive deeper into different subsystems involved in the project, starting with propulsion. The COTS motor selected for APJ-III is an Aerotech M2500T. It is an APCP-based 98mm reloadable solid rocket motor, which will take a rocket close to the desired apogee in around 25 seconds. Using open rocket simulations with the weather parameters set to far side, a rocket is expected to reach an apogee of 10,813 feet. Since Open Rocket does not take account of variable wind speeds, and the final production of the various subsystems will render the launch vehicle a bit heavy, this overshooted apogee is then compensated and brings us close to 10,000 feet. To tell you more about aerostructures, here's Sangram and Tanmay.
Thank you, Aasit. Hello, my name is Sangram Jadhav, and I am the Aerostructures lead at STES Rocketry Team. So herein you can see our design. It is mainly made out of carbon fiber and fiberglass. The whole airframe is divided into 4 sections: the nose cone, upper airframe, main chute tube, and motor tube, and is manufactured by using a wet lab process on a cylindrical mandrel. The outer diameter is 154 mm and the total length is 2.18 meters. The dimensions were finalized considering that all the subsystems could easily fit inside the respective tubes. Now we'll start with the nose cone. It is a half parabola power series carbon fiber nose cone, which is to be manufactured by a wet layer process on a 3D printed mold designed by the Aerostructures team. You can observe a nose tip on the forehead, which is manufactured out of aluminium to have a symmetrical shape at the top and also to sustain high temperatures during flight. The tip is connected to the body using bolt and plate configuration as shown in the adjoining figure. The nose cone also includes an elongated section of the same body diameter that houses the drogue recovery subsystem. So now, to join two body tubes as well as mount different components, bulkhead shell couplers were designed instead of using traditional couplers. The two types of bulkheads which we are using are coupling bulkheads and supporting bulkheads. Coupling bulkheads, as the name suggests, are used to join two body tubes and are connected to the parachutes through eye bolts. The bulkheads are thoroughly tested by using simulations with the shock loads calculated. The thrust bulkhead is also checked by simulation analysis whether it can sustain the loads without deformation. The second are supporting or mounting bulkheads. They are nothing but to support and mount different subsystems in a rocket. There are in total 7 bulkheads, out of which 6 are made out of aluminium and one being a centering ring out of delrin. So this kind of mechanism was used in previous iterations of the rocket, which connected the different body tubes tightly with zero flex and was strong enough to sustain the normal and the axial loads on them. So herein you can see few simulations done on different bulkheads. Now our colleague Tanmay will explain the subsequent parts.
Hello everyone, my name is Tanmay and I'm the co-lead of Aerostructure at STES Rocketry Team. The second component of our rocket is upper airframe. Upper airframe is again divided into 2 sections, one containing avionics and other houses payload subsystem. And this tube is differentiated by others as it is made up of fiberglass, and it should transmit the flight data via telemetry over radio frequencies, which was not possible by carbon fiber. So hence, fiberglass is used instead of carbon fiber. Now next component is our main chute tube. Now main chute tube houses our main recovery systems like our main parachutes and shock box, and it is located at the lower end of airframe. And this tube is the manufacture of carbon fiber. Next comes our motor tube. Motor tube consists of COTS motor, thrust and motor retention bulkheads, centering ring and fin assemblies. And these fin assemblies are assembled at the rear end of the motor tube. And a motor tube is also the manufacture of carbon fiber. Next comes our fins. Now, after various studies and simulation on open rocket, the structures team settled on using 4 fins of clip delta configuration and dimensioning it on the basis of thumb rule, which also contributed to sufficient stability. Subsequently, fin flutter calculations were done using different material, out of which aluminum was selected, considering various difficulties during manufacturing and shipping. To hold the fins in a place, the fin mount, which is also the manufacture of aluminum, are used and held tightly using nuts and bolts. A fin can, which is the manufacture of Delrin, is placed inside the motor tube, into which the fin mounts are bolted. And in the adjoining figure, you can see our fin assemblies. So that's it for structures design details. The recovery part is handed over to Pranav.
Hello everybody, I'm Pranav and I'm the recovery lead at STES Rocketry Team. Today I'll be discussing about the recovery subsystems. So APJ-III is required for the dual deployment system with the drogue chute deploying at apogee and the main chute at approximately 1500 feet above ground level. The primary charge is triggered at apogee for drogue chute and at 1500 feet for main chute. The backup charge for both chutes have a 3-second delay. About the parachute details, the drogue chute is of an elliptical shape with a drag coefficient of 1.5 and with a descent velocity of 29 meters per second after deployment. The main chute is of a toroidal shape with a drag coefficient of 2.2 and with a descent velocity of 6.84 meters per second approximately after deployment. And both the parachutes are manufactured by Fluid Chutes. About the ejection system, the pyrotechnic ejection method was used for the ejection. Both primary and backup charges have a 4-gram charge in fate, and the combustion of these charges will produce a pressure of 24.67 psi, successfully ejecting the parachute. About the recovery hardware, the shock cords which were used were of 2 different lengths. A 30-feet shock cord was used in the drogue chute compartment and a 25-feet shock cord was used in the main chute compartment. Both of these shock cords have a breaking strength of 40 to 100 pounds. The quick links used have a working load of 875 pounds and the swivel links have a working load of 1200 pounds. So that's it for recovery, and we'll move on to avionics.
Hi, I'm Shantanu, the avionics lead for STES Rocketry. The SRAD avionics consists of a buck converter as a voltage regulator to regulate the 11.1 volt lithium ion battery to 5 volt and 3.3 volt. An Arduino Nano is used for controlling the system and triggering events such as successful arming, deployments, etc. BMP280 is used for pressure, altitude, and temperature readings. SAM-M8Q is used for locating the rocket for recovery. Catalyx SD card module for onboard data logging, and Zigbee S3B Pro equipped with high gain antenna for the telemetry system. The SRAD altimeter also supports dual deployment. The ground station consists of a Yagi-Uda antenna for receiving telemetry data from our SRAD telemetry solution. The data will be forwarded to the ground station Zigbee S3B Pro placed on an adapter, which is connected to the serial port of the computer. The desktop application running on the computer is connected to the serial port, which will display the data sent by the telemetry system. The ground station also consists of COTS featherweight tracker for receiving data from COTS GPS solution and forwards the said data to the mobile application that comes with the device. Here's Piyusha, an avionics technician at STES Rocketry, to tell you more about the COTS hardware.
Hi, I'm Piyusha Patil and I'm avionics technician at STES Rocketry Team. This year, we have decided to use Perfect Flight Statologger CF as our primary and backup altimeter solution, along with the featherweight GPS tracker as our primary GPS solution. Statologger was chosen because of its ability to handle dual deployment system, small form factor, and low power requirement, whereas featherweight was chosen because of its ham licensed free frequency range and detailed data logging for post-flight analysis. Lastly, arming of the complete avionics system is handled by 2 DPST switches. The first switch arms the SRAD altimeter and featherweight GPS, and the other switch arms the 2 COTS altimeters. To acknowledge successful arming of the SRAD altimeter, a buzzer installed on said altimeter goes off for the duration of 3 seconds. To talk about the payload, I hand over control to Shantanu.
Hello, so my name is Shantanu. I'm a payload engineer at STES Rocketry Team, and OATMEAL is our modular payload concept for the ASIC Cup IREC 2021 season. OATMEAL is a compact muon detection payload of 3 form factor weighing approximately 9 pounds based on MIT's Cosmic Watch desktop muon detector program that will execute the mission objective of in situ detection of cosmic ray muons throughout the sounding rocket's flight. The payload has been divided into 2 key components, the muon detector itself and the payload DAQ system. The muon detector is at the heart of the payload subsystem, and it operates on the principle of measuring electrical signals produced by ionization of highly energetic subatomic particles via the process of scintillation. The functional block diagram given below illustrates the working of the muon detector in a simplified manner. Subatomic particles initially make contact with the ionizing material doped plastic scintillator slab, depositing some of the energy in the form of photons. After considerably amplifying the photons, these photons are then collected by a silicon photomultiplier, which generates an electrical signal. The signal is then routed to a main PCB, where it is amplified by surface-mounted amplifying electronics. The peak of this newly generated signal is then compared to a software-specified threshold by a peak detecting circuit on this PCB. If it crosses the threshold, then all measurement data, such as the timestamp, measured voltage, and so on, are processed by an Arduino microcontroller and recorded on an SD card. Two similar detectors are utilized in master slave or coincidence mode to reduce the error rate of detecting particles that are not muons. Further, to reduce the possibility of noisy measurements, the detectors are placed within aluminum containers, which are subsequently housed inside cube-shaped boxes constructed of plain carbon steel. Finally, this entire setup and is powered up by a 11-volt lithium-ion battery source, enough to keep the detectors working for a long period of time. The payload DOQ is the second component of the payload subsystem, and it collects spatial data that may be used for analysis of the muon detector's observations as well as determining the rocket flight's results. The payload DOQ system comprises of an Arduino microcontroller interfaced with pressure sensors and accelerometers mounted on the rocket hull through Molex connectors to measure altitude and rocket orientation in addition to the detector's operation. This system is also housed inside an ABS plastic cylinder and is powered up by 11.1 volt 3 S1P battery sources. Finally, the payload subsystems measurements will be processed and analyzed in respect to the Reisner-Forger curve and the Param model. In a nutshell, both of these graphs show that the count rate of the radioactive subatomic particles increase with the rising altitude until a saturation point is reached where no new particles are generated due to a lack of atmosphere. Despite the fact that both these curves are created at extremely high altitudes and the count rate is generally determined for all types of radioactive particles, it is safe to use them as a baseline because muons make up the majority of particles generated by secondary cosmic rays. As a result, our hypothesis is that we will receive a curve similar to either one of these, and if we do, then the payload experiment will be considered a success. To conclude with this presentation, I would like to call upon Aasit once again.
This year was one of the most challenging years the team has ever faced. The college was closed since last March, and only limited students who run their own team were allowed on premise. Due to this, only a limited amount of tests that were necessary were done, and rest were either theoretically finalized or were entirely put on hold. Even though the progress was slow this year, the team made certain that it did not stop. As a result, we made a design that is as close to manufacturing and flight ready as possible. Big thanks to everyone at SRAD to have us participate virtually this year and having us showcase the design. And we hope to implement it full scale again in the next flight event.